So my last lesson was about 6.3, the mole and the chemical equations. Now, chemical equations clearly tell us how many moles of reactants react to form how many moles of products. And the idea is really very simple. Balanced chemical equation helps you with it. And these are actually very easy numbers. Take a look at this equation. 1 mole of iron reacted with 1 mole of sulfur produced 1 mole of iron sulfide. The same thing is mentioned over here, here, and here, which means they always have these ratios in terms of moles. Not just that, we clarified the last time that law of conservation, and I'm going to complete it, law of conservation of mass is applied to this portion, which means 56 gram of iron, which is, by the way, mass of iron in the periodic table, reacts with 32 grams of sulfur, which is the mass of sulfur in the periodic table, gives us 88 grams of iron sulfide. And here 88 grams is actually its MR, the molar mass we usually calculate from the periodic table. Now, if you're going to add up these two numbers, you're going to see they're exactly equal to this one on calculator. That means we can always go with ratios, the ratios as per moles and the ratios as per mass. And both of them are actually correct, which means we can scale them up or scale them down, right? Let's scale it up. If 1 mole of iron reacts with 1 mole of sulfur produces 1 mole of iron sulfide, then 10 moles of iron and 10 moles of sulfur would produce how many moles of iron sulfide? What do you think? It's a really easy ratio. The numbers are supposed to be the same throughout the equation. So it was 1, 1, and 1. Now it's going to be 10, 10, and what?
10.
Right. Easy enough. Now, if I take 100 moles of this and 100 moles of this, how many moles of iron sulfide am I going to produce?
100.
100. Perfect. This even works for math. Let's say instead of 56, I take 560 grams of this. Instead of 32, I take 320 grams of this. So instead of 88, how many grams will I produce? Don't use the calculator, please.
80.
Right, 880. That's a very simple working. I added 10 over here, 10 over here, and of course, another 0 over here. Now, if I take 5,600 grams of iron and then I take 3,200 grams of sulfur, how many grams of iron sulfide am I going to produce?
8,800.
8,800. I think you can easily scale it up or scale it down. Since we have been only doing the examples of scaling it up, let's do an example of scaling it down, which actually is a part of the book. Now, let's consider this. If I take, instead of 56, I take only 5.6 grams. Instead of 32, I take only 3.2 grams. So how many grams of iron sulfide would I produce? 8.8. Does it make sense? I have now, instead of adding a number, I've added a decimal right in between those two numbers I was using previously. So that's how I end up with 56 to 5.6, 32 to 3.2, and 88 to 8.8. Now this is known as scaling it down using smaller amounts. Right? Make sense?
Yes, sir.
So that means it's really very easy to work these out. Now, let's go with the different equations as we have been working a lot on the same equation already. So calcium carbonate and calcium oxide produce carbon dioxide. Calcium carbonate produces calcium oxide and carbon dioxide upon thermal decomposition. as says in this line, which means whenever we heat this one up, this actually breaks down into two components, which are calcium oxide and carbon dioxide. Now, 1 mole of this produces 1 mole of this and this, right? If I have 10 moles of this, how many moles of calcium oxide and carbon dioxide am I going to produce?
10 moles.
Right, 10 moles each. 10 moles of this and 10 moles of this, right? So that's pretty
Yes.
much understandable. The mass to this one, the MR is 100. The MR in this case is 56. The MR in this case is 44. So if instead of 100 grams, I take 100 tons of this, and now we are really scaling it up. We are talking about industrial level, because at industrial level, we deal with in tons. So of course, I'm going to produce 56 tons of this and 44 tons of this. Make sense?
Yes, sir.
And if I have 10 tons of calcium carbonate, I would produce 5.6 tons of calcium oxide, and of course, 4.4 tons of carbon dioxide. I hope that makes sense too, because we are really scaling it into many different scales, sometimes too much larger, sometimes too much smaller, sometimes something in between. I hope all of this does really make sense to you, right?
Yes, sir.
Great. If this makes sense to you, I'm going to come up with a mathematical method of solving the questions, which might seem difficult at any point. So I'm going to stop sharing the book. Instead, I'm going to share yesterday's work. So getting it on with the yesterday's work. Yeah, there we go. So yesterday, I was actually talking about the same equation we recently dealt with. Calcium carbonate upon heat breaks down into calcium oxide and carbon dioxide. My question was, how much of calcium oxide is produced in kilograms if 2.3 kilograms of calcium carbonated is thermally decomposed? Now, what we are supposed to do in this kind of question is that we first need to come up with ratios. We come up with ratios by putting the MRs. So I wrote the equation, I balanced the equation if needed be. Since this equation is already balanced, so I'm not going to balance it again. And I simply went on with writing the MRs. Writing the MRs actually give us the mass ratios. So you can see we have the mass ratio over here. The MR is 100, this MR is 56, this MR is 44. So what do I have? Calcium carbonate. The information I have is related to calcium carbonate over here. So I write that on my left. What do I need to know about is calcium oxide, because that is what have been asked in the question. So I write then on my right hand side. I first of all write their MRs. That means 100 grams of calcium carbonate, when decomposed, produces 56 grams of calcium oxide. But this time we are supposed to decompose 2.3 kilograms of it, not just grams. And I don't really know what it's going to produce, so I put that value as X. Now, what I'm supposed to do is that I'm supposed to put a dividing sign in between both the values. I take the X over here, the other values over there. 100 grams come as a denominator. 2.3 kg goes on the other side as numerator. 56 grams stays over there. X goes on the other side and numerator. So X is equal to 56 grams into 2.3 kilograms multiplied by 100 grams. We can cut the unit grams on top and bottom. What are we left with? Numbers. If we actually work with these numbers, 56 multiplied by 2.3 divided by 100 give us the answer in 1.288. Since kilogram is the only unit left, we can write it over here, and that's the amount of calcium oxide that is actually produced. So this is known as ratio method and metric method. Both the names represent the same thing. This method is what we were really doing in the book right now. And this method is really going to help you a lot with the questions. The questions
Yes, sir.
in which math or same units or same quantities are actually present on both sides. These questions really work if you are taking math on this side. Let's say it can be any units, gram or kilograms, and math on this side. That kind of conversion works for ratio method or metric method. That's why we use it. Then I quoted another question using the equation in question number 1. how much of carbon dioxide is produced in grams if just 25 grams of calcium carbonate is decomposed. So 100 grams gives us 44 grams. This time we're talking about carbon dioxide. So that right-hand side really changes. So 100 grams produce 44 grams. 45 grams would produce what? That's X. Put up the values, you get your answers. You see the answer comes out to be mass of carbon dioxide to be 11 grams. Make sense?
Yes, sir.
Great. Looking at this question will give you a very good idea of how it goes.
Yes, sir, I have understood it.
Good, good. Then let's clear everything up and let's move ahead. There was one more question. The question is given in black. The solution is given in red. There is a key to the steps you should take to answer your question. So go ahead, read the portion in black first, then read the portion in red. Let me know if you are not able to understand anything. Take your time. So calculating reactant amounts or producing a product amounts using a chemical footbridge. As this diagram explains us, chemical footbridge is actually a sequence. We also call it up across down bridge, and it really gives the student the idea or the number of steps he or she needs to take in order to get their answers. So usually what happens is that you are given with mass of any of the reactants, and you first convert it into reactant, moles of reactant. This is really the up step, as he said before. Now, you use the ratio from the equation, you convert the moles of reactants into moles of products, and this is really the across step that we were talking about. And the moles of products are then finally converted into mass of product, and this is the down step he was talking about. So it really works like a bridge. You go up the bridge, you go across, and then you go down, and you actually cross a bridge. We call it a footbridge. So the footbridge works in the similar way. So there are three main steps. Conversion from another quantity to moles. This is usually the step one, which is a formula step most of the time. And then there is a ratio step through which we convert one moles of one reactant into another reactant, maybe into a product. This is the second step. This usually is the ratio or the metric method based step. And then finally, we convert those moles of reactants or products into their mass or any other quantity. Since this is shown with mass, that's why I'm talking about mass, but it can really be anything. It can be number of particles, it can be volume of a gas, it can be concentration, it can be anything. Since this is the simplest form of the footbridge, they're just talking about masses alone. But in the later parts of the book, you're going to understand and you're going to go through with those questions in which you actually convert one kind of quantity into another kind of quantity. So mass of reactants and mass of product can really be done with only the ratio method. So we don't need to use this method for this purpose. However, we can use the conversion into one quantity to another, one type to another, and that's what really this up across down bridge is all about. So the third step also tends to be the formula step, and that's how we are capable of converting them into different quantities. So I'm going to go with an example, a worked example that is given over here, worked example 6.6. So what mass of aluminum oxide is produced when 9.2 grams of aluminum metal reacts completely with oxygen gas? Now take a look at this equation. This is the equation. The equation has already been balanced for us. Now the ratio of aluminum to aluminum oxide is 4 moles of aluminum produce 2 moles of aluminum oxide. However, we have 9.2 grams of it, so we can convert it. Now remember, this question, since this question is about mass over here and mass over here, so I do not suggest you to use footbridge for it. Since the way it can be done is a perfectly good way if we only use the ratio method. If we don't use the molar ratio, instead we just use the mass ratio. This is 27. We multiply it by 4. This is 32. This is actually 16 into 2 is equal to 32. So I should better write 32 like that. So it's actually 16 into 2, which is 32, and into 3 then. And we have this 27 into 2 plus 16 into 3, and that's 4 is multiplied by 2. So you're going to find out that this 27 into 4, that's, I guess, 108. And 16 into 2, 32, that's 96. And the whole comes out to be something like 204, I guess. If I'm right, yeah, that would be 204. So that's how it works. 108 grams of this produces 204 grams of this. So 9.2 grams would produce what? So that's 108, 9.2 ratio 204 AL ratio AL to O3 over X. And you can really find out this way. So this is a much quicker way of doing it. So X would be equal to 204 into 9.2 divided by 108. You can always find out the answer, right? You'll find out that the value of X through this method and the method given over here in terms of entire up across down bridge, up bridge where he converts 9.2 into moles, across bridge where he takes the ratio of those moles and find their answer. So I'm going to clear this part up. Instead, let's not clear it up. Let's go in the same way. So moles 0.17, 0.17 multiplied by 1 or 2. This gives you the idea of 17.3 grams. So I hope if you use it, and if you have a calculator, help me with this. 204 multiplied by 9.2 divided by 108 is the answer. 17.3 for this one as well.
Sir, I'm going to do it.
Yeah, take your time. I can wait.
Yes, sir, the answer is 17.37.
So that is 17.37. So it gives you almost the same answer that you get over here. So it is not necessary that you go with the footbridge over here. All right, you can use the metric method, since metric method is something that you're going to find faster. Okay, so if we really talk about this in this way, you will understand that this method is a faster method. But why am I then stressing about footbridge? I'm only stressing footbridge for the purpose when you have different quantities to handle with. For example, he actually started off with the whole question in terms of aluminum. What if he discusses the same thing with oxygen in terms of volume? What then? Then you might not be able to use the ratio method, and you will have to use this footbridge alone, and you will have to rely on footbridge. Let me clarify myself by giving an example. Let's suppose instead of taking this as a piece of information, we say that we used approximately 72 decimeter cube of O2. And how much aluminum oxide, mass of aluminum oxide is produced. Now, instead of having grams over here, we have 72 decimeter cubes of O2 over here, which actually I should write below O2. And I still need the other value in mass. Now, these are two entirely different units. As soon as I say the word decimeter cube, you understand I'm talking about volume over here. And here I'm talking about mass, and probably I'll need the value in grams, right? So now in this kind of case, you are stuck with footbridge. Metric method won't work. Yeah, metric method can be improvised for this kind of working, but usually at this level, we do not tell it to students because it becomes a little bit complicated. So it's better to go with this. Then what you are going to do is that you follow all these three steps. So what is step one? Step one is that you put the formula. So here the formula is equal to moles is volume, and I should do it over here since at this point you might not be able to see it over here. So I'm going to do it on this side. So moles is equal to volume over molar volume, right? That's first step, and that's up step. You may call it step one, whatever you like. So we understand the volume is 72 decimeter cube, and molar volume for any gas on the planet is 23 decimeter cube per mole. I hope you remember this value. So really decimeter cubes cut down, it comes out to be 3 moles. That's step one. Now the across or step two, which we casually do, is the molar ratio. The molar ratio is something he has already done over here for aluminum, but we're not going to do this because we need the molar ratio O2 ratio Al to O3. Now we understand 3 moles of O2 produce 2 moles of Al to O3. And luckily, we already have 3 moles of O2. That means we do not need to work it out. I actually intentionally gave you an easier question so that you don't have to work a lot on the ratio. Since it's 3 and 2 over here, luckily it's also 3 over here, so we do not need to work it anymore. So lastly, we have the down step, which is the third step in this case, third and probably the last step as well, which is again the math. Now, in this case, if we have 2 moles of this, so 2 moles, actually, I should write the formula first. You might not be ready without the formula, so I should write the formula. So here, mass is equal to moles into mR. That's what the formula is. And since we have 2 moles, and I'm gonna turn that into red so that I can really use the value over here. And that's what I'm gonna use over here. Okay, so 2 multiplied by mR. mR was, I guess, 102. I should write it over here, shouldn't become a problem. 27 into 2 plus 16 into 3, that's actually 54 plus 48. The answer is equal to 102, right? So that's how it becomes 204 grams, right? So this whole footbridge actually helps us to get our way with numbers, and this talking about this specific kind of question actually to work with different quantities. So is this understandable for you?
Yes, sir.
Okay, good. So have you been through these questions or these kind of questions before?
Sir, not for the volume questions, but for the other questions, yes, I've been through them. Where we have to use the ratio and then we have to divide it with a furthermore with the mass.
Or with other formulas, right? Good. If you need to work with the ratios and with the formulas in a single question, then that means you have been through these kind of questions.
Yes, sir.
All right, great. So Wes is here, so I'm gonna make sure that Wes understands this too. Okay, Wes, this seems like complicated stuff, but I'm going to make sure that you understand it. Ready?
Yes, sir. Okay.
Okay. So I changed this worked example 6.6 on your left. So I'm gonna read out the change statement for you. So what mass of aluminum oxide is produced when the original question was about 9.2 grams of aluminum metal? Instead, I changed it with the value of 72 decimeter cubes of oxygen. Now, as soon as I say the word decimeter cube, what should come into your mind is that we are working with volume, as I've written on your extreme left. All right. So we have the value for volume and we need to find out the mass of the product. This means we are working with two different quantities. So Footbridge is actually the way of solution, the way to work between these values. So what do we do? First of all, we need the balanced chemical equation, which is given over here on your left. 4 moles of aluminum plus 3 moles of oxygen gives you 2 moles of aluminum oxide. I'm going to clear this up so that it's easy for you to read and understand. Okay. So now, in this case, although this question has been done with 9.2 grams of aluminum, but I solved this question separately for different set of values. Why? Because this question has been solved for mass, for which yesterday we understood the metric or the ratio method. That's good enough if you have masses on both sides. You don't really need to use footbridge for that purpose. Footbridge is used for the purpose when you need to work with two different quantities, like volume and mass, or like number of uh, particles or mass, or like concentration in mass, or like concentration in volume. So any case is possible, but if there are two different quantities, use what I'm about to tell you. Okay, so you have this balanced chemical equation. You understand 4 moles of aluminum reacts with 3 moles of oxygen to produce 2 moles of aluminum oxide. You have 72 grams decimeter cube of oxygen to work with. So that's how your footbridge is going to work. Now, footbridge has 3 steps. Step 1 is commonly known as up step. Step 2 is commonly known as cross step. Step 3 is commonly known as down step. Let's start with step 1. Step 1 is usually a formula step. The formula moles is equal to volume over molar volume has been used over here. Why? Since the quantity has been given in volume, we need a formula with volume. So that formula says that whatever volume you have divided by molar volume. And since I've already explained, any gas on the planet is actually 24 decimeter cube per volume, decimeter cube per mole. So that's the value of molar volume for any gas on the planet. We already know that value, so we put it as the denominator. The numerator is the volume of oxygen itself, 72 decimeter cube. From there, we have moles of oxygen. Once you have the moles of oxygen, you're done with step 1. You move on to step 2, the cross step. The cross step says that you need a ratio in between oxygen and aluminum oxide. Now, on your left-hand side, there has been a ratio portion solved, but this was solved for aluminum and aluminum oxide. See, the number 4 is for aluminum, which is represented over here. Number 2 is for aluminum oxide, which is represented over here. But since we're not working with aluminum and aluminum oxide, we are working with oxygen and aluminum oxide. So we need to write down their ratios. So you might notice that right under the cross portion on your right hand side, I have written oxygen ratio aluminum oxide. And the ratio number for oxygen in the equation is 3, which is written over here. So I quoted it down over here. And those of aluminum oxide are 2 in the equation. So I quoted 2 over here. We usually solve it by writing more values, but since we have 3 moles in here, I'm gonna color that portion up. So we don't really need to go for the second step, since the value given in the question is actually the value we have. So this already tells us that if we have 3 moles of oxygen, we're going to produce 2 moles of aluminum oxide. All right, make sense?
Uh, yeah, kind of, sir. But I think if you do more examples, I suppose we would understand. I'd get it more.
Yeah, it always works like that. Footbridge questions are usually not completely comprehensible in the first go. So the more examples you do, the better you become at it. So for starters, if you do get the point, we have 3 moles of oxygen and we would be able to produce 2 moles of aluminum oxide. So that's good enough for being a starter, right? Then we actually come to the third step, the down step. in which we need to find out the mass in grams of aluminum oxide. Now we already know we have produced 2 moles of aluminum oxide. So if we have the moles, we multiply them by MR and we get the mass as per the formula. So let's apply that formula. So there are 2 moles and we need to calculate the MR of aluminum oxide, which I did right over here, and which tells you that aluminum oxide MR is 102. So I multiply that 2 by 102 and I understand that I would be able to produce 204 grams of aluminum oxide, right?
Yes, sir.
Okay. So this is the kind of stuff which we find difficult when we deal with it in chemistry. So I always tell my students, if these numbers start to confuse you, you should start taking them as money. I tend to say that because we are always good when we are handling money. All right. Okay, let me quote an example. I'm supposedly going to go with an example that might work better with Wes or with actually both of you. Okay. So let's say you are given with 1,000 reals. Okay. And let's say your favorite shirt is 2,000 reals each. All right. And let's say something else. Let's say some of your stationery item. I can't come up with any, so I'm gonna just assume it's a stationery item, and that's actually 50 SAR each. Okay. So if you want to make a different set of combinations, the first combination that you can come up with by consuming the whole 1,000 SAR, what would that be? How many shirts and how many pieces of stationery would you be able to buy to completely consume your 1,000 real in your only trip? These kind of questions can really help us with the mole questions. Let's quickly see whether you both can come up with an answer. And your combinations can really be different. One of you may prefer more shirts, one of you may prefer more stationery items. So how many stationery items and how many shirts would you be able to get if you consume the 1,000 SAR you have been given with completely? And you have to purchase both things. Doesn't matter what number you purchase them in, you have to purchase both things. Come on, that should be easy.
Four shirts and
Okay, so you say that you'd buy 4 shirts and how many pieces of stationery?
four
4 pieces of stationery. Good. What about you, Wes? You may have a different set or you may have the same set. It's entirely actually your priority, how you deal with it. Whether you like more shirts or whether you like more pieces of stationery,
So I'll just buy 4 shirts.
right?
Sorry, 5 shirts.
It means you don't need any stationery. You love shirts so much. You're not going to buy any stationery.
No, sir.
Okay, all right, good. So I hope you understand the point I'm trying to make, that if you have been given something to start with and some 2 different kinds of values to work with, you can always go with some simple multiplication, addition, subtraction, or these simple arithmetic operations to calculate how many of in each thing, maybe 2 different options or 3 different options you have, you're going to buy, right? So when we work with money, we are actually more conscious, we are actually more mathematical, and we can work our way out. I've seen students do a lot better with money than any other set of numbers they are given with. So if you ever get confused, it is pretty simple that if we start with 4 of this and 3 of this, we're able to buy 2 of this. So if I don't start with 4, I start with 8 of this. So of course I will need 6 of this and I'll make 4 of this. Make sense? It's actually scaling. Pretty much the same thing we are used to do with money. So don't get confused with this kind of working because it is almost the same stuff. It's just that it gets boring with chemistry. With money, it's interesting. You're getting something out of it. You are working on it consciously and maybe with more interest. But as soon as we need to work with boring chemicals, it becomes uninteresting and we really lose focus at time. I hope you agree with me, right?
Yeah. Yes, sir.
Yeah, I understand how boring that is. But I hope this makes sense to you that how can we convert or play with numbers, or heck, how examiner tends to play with numbers and tries to sort the students or filter the students on basis of how good or bad they are when they have to deal with numbers like this, right?
Yes, sir.
Great. If you both understand it, then that's good. And I'm going to get to this study tip. Remember to take the balancing numbers into account while making your calculation. This is known as psychometry. It's also pronounced as stoichiometry of the equation. This is what quantitative chemistry is all about. We also call it stoichiometry. That means we take balanced number chemical equation numbers and we use them in order to calculate anything. Okay, so what I'm going to do is that I'm going to come up with an example and I need both of you to solve that example. Okay, all right. Mm, let's share the whiteboard. Okay, so how many grams of, let's see, water produced when 100 decimeter cube of ammonia is reacted completely with oxygen as, and I'm already going to write a balanced chemical equation for you so that you don't have to waste your time with it. You can simply work out the values and let me know the answer. How many grams of water are produced when 100 decimeter cube of ammonia is reacted completely with oxygen? There you go. Take your time. Remember, you have to do 3 steps, and I'm going to write your steps for you. Number 1, you need to find out moles of ammonia reacted. and your answer would come out in the unit of moles. Number two, the second step you're going to do is to find out moles of H2O produced. And that answer is also going to be in moles. And number three, mass of water produced. And that is in grams. I'm also going to help you with this, that this is a formula step. You are going to apply a formula over here. This is a ratio step. And again, this is a formula step. That's how most questions would go. Go ahead. This is enough of hints for you. So now I hope this would be easier for you. Take your time. When you're done, let me know. You can even let me know step by step what your answers are.
Thank you.
And remember, these rules actually go for entire quantitative chemistry. Whether you're solving a moles question, or you're going for empirical formula, or you are going with a percentage composition, anything out of quantitative chemistry is done in the similar way. Don't keep rounding off your answers at every step. That way, you are never going to reach the accuracy you want to. Right? And three significant figures is the minimum rule. You can go with anything higher. You can go with four significant figures or five significant figures for your own accuracy. That's up to you. But three or four are the most used ones. Well, well done. Yes, the answer is 4.16 moles for the first one.
Part
Okay, you are saying 4.40. 4.40. Does not seem right. Okay, let me just check and be on the safe side. You were saying that you got 4.16. The answer to part one by using the formula mole is equal to volume over molar volume, right? And that was 100 divided by 24. And that's how you got your answer of 4.16 moles. That's for the first part. For the second part, I hope that you used NH3 ratio H2O, right? And you use the numbers given in the equation first, which are 4 ratio 6, and then you use this number 4.16 ratio X. You divided them. X turned out to be equal to 6 multiplied by 4.16 divided by 4, 3, and 2. And that's how the answer turned out to be 4.4, right?
No, sir, I made a mistake.
Yeah, I guess it's 1.5 multiplied by 4.16, and answer is going to be 6 point something, 6.24. I don't have the calculator with me. That's why I'm not exactly able to get to the decimal points right, but I guess
Yes,
this
sir.
is the
The answer is 6.24.
6.24. All right, great. So it's not 4.40, it's actually 6.24 moles of water. So we can definitely find out the math. This is part one. This whole thing is part two. Let's see what you get for part three. And you're done, let me know. Part three is actually easy. 112.32 grams. Okay, let's see. I hope you have multiplied 6.24 by 18 to get your answer,
Yes,
right?
sir.
And the answer is 112.32. That's perfect. That's because we multiply the number of moles by MR, and that gives us mass. So that actually mass is equal to mole into MR. That's how we get part three's answer. Okay, that's great. That means you get a hang of it. So I'm gonna change it to a little bit of a different situation. Since the situation you just faced was much closer to what we did before on the book, you have been given volume and you find out the mass of the product. What if the reverse is done for you? Okay, so I'm going to use the equation in from the question one, but we are going to change the way we ask the question. So for question two, using equation in question one, okay, this is kind of like reverse footbridge. This time, what I've asked you is a quantity of a reactant when you're given with a quantity of a product. Okay, so this is slightly different in terms of how the question is asked, but how you work out your answers or really the steps, they're not different at all. So let me tell you what the steps are. Step one, moles of NO produced. Instead of reacted, since we are starting with reverse, so it would be produced comes first, but that doesn't really matter since we're handling with numbers. So whether we are going from the reactants to products or from products to reactants, it really does not matter. So you would notice that the way I am writing the steps is still pretty much the same. So moles in first step, moles in second step, and whichever quantity I have asked in the question comes out to be third, which is mass of oxygen reacted. So it's just the difference of reacted and produced, which comes first, which comes after. There you go. And of course, formula step, ratio step, formula step. That's how it's going to work. When you're done and you come up with answers, let me know. Perfect. You're right. The answer would be 4.16.
Okay, sir.
All right, Wes, can you hear me?
Yes, sir.
Okay, start doing question number 1. And since the solution is also written over here, so it would really help you with what you're doing. Solution to part 1, part 2, and part 3 have been bifurcated over here, though that's very small in font, but I hope you're able to get it. But if you're not able to get what I've written over here at any point, do let me know. All right?
Yes, sir.
Take your time
Okay.
to understand it, and then you can continue with question 2.
Okay.
Sir, is the answer 5.2 for the second part?
5.2. Okay, I hope that you did the same for mole is equal to volume over molar volume in first part. That is 100 over 24. And that's how you got your answer of 4.16 moles. Just to be on the safe side, part 2, you took O2 ratio NO, and that came out to be 5:4, and then 4.16 ratio X. Then when you want to solve X, it would become 4 multiplied by 4.16 divided by 5. So the answer comes out to be what? Can you repeat?
Sir, the answer in the calculator is 3.3. I basically did the same thing, but I wrote 4 ratio 5 divided by 4.16 over x.
This is a little bit difficult for me to understand. And when you rearrange it to get the value for x, do you get the same equation that I've written over here?
No, sir, I got 5 multiplied by 4.16 over 4. Basically,
Oh,
I wrote
okay,
4.
okay. Yeah, I guess you're right. I made a mistake. I am understanding the point that since the question was asked differently, I made a mistake. So, okay, so oxygen is something that we need to find out, and NO is something that we have been given. So that's ratio 4:5 and 4.16 ratio X. So X is equal to 5 into 4.16. Wait a second. Over 4.
And the
That,
answer is 5.2.
yeah, that way the answer is not going to be 3.38. So since we have the value for NO would be on left. Since what we need to find out is oxygen, so oxygen is going to be on right. The value of NO in the equation is 4, and the value of O in the equation is 5. The previous answer calculates the number of moles of NO to be 4.16, and X is what we need to find out. That's why it's X. O2 is what we need to find out. That's why it's X. So X is equal to 5 into 4.16 over 4. I think that's, now we are right. And the answer in this way is
5.2.
5.20. Remember, 3 significant figures, so 5.20. Is your calculator also giving you 5.20? Because
Yes,
5.2 only means 5.20.
the calculator is giving 5.2, so we will add the
Yeah,
0.
yeah, of course, that means 5.20 in order to get to 3 significant figures. Okay, that's how it works, fine. Let's get to part 3 now. I hope you have already made corrections to part 2. Okay, what about Wes? Wes, are you following? Question number one. Do you get how we did question number one? Because it's exactly similar to what we did back on the book. It's just a different equation we're dealing with, but the process is almost the same.
Sir, I got 166.4 for the last part.
166.4. Let's do it over here. That is mass is equal to mole into MR. And of course, moles are 5.2. MR is 32. Yeah, that's perfectly correct. 166.4. That is right. That is equal to 166.4 grams. Right?
Yes, sir.
Good, which means you get a hang of it. Now let's see where Wes is. So Wes, what about you? Are you doing okay?
Sure, I'm kind of confused, and yeah, I'm kind of confused.
Can you elaborate it a little bit? Is it part one, part two, part three, anything in specific or as a whole?
Sure, as a whole.
Okay, let's go with the question step by step. Let's cut it down into a few smaller parts to get it right. Ariba, if you think you have already understood it, take a 2 to 3 minutes break. You may drink water, you may take a stroll, freshen up a little bit, and me and Abbas are going to work at it, right?
Right,
But
sir.
do take just a few minutes stroll, be back quick. Okay, so
Yes, sir.
Wes, how many grams of water are produced if 100 decimeter cube of ammonia is reacted completely with oxygen according to this equation? Now, the equation has already been written and is balanced for you. Also, the steps are mentioned, what you need to find out at every step, which means the Footbridge steps, step one, step two, step three, have already been given to you in the form of directions. I have done this not to give you a hint. I've done this because Cambridge does the same in exams. If you're going to pick up past papers, you're going to see that they actually give you hints like this, what you're supposed to do in step one, what you're supposed to do in step two, step three, and so on. And of course, the units are also written in the paper. The only hint I gave you is written in the brackets. The first step is a formula step, the second step is a ratio step, the third step is a formula step. These three written in brackets are actually my set of hints for you. Okay, so let's start with the very first step. They tell you that whatever the information is given about, and let me tell you the information is given for ammonia over here. So the first thing we need to do is to convert that information into number of moles of ammonia, right? And that's written in the first point. There it is. So what do we need to do? We need to apply the formula. The formula for moles would be according to the units that you see over here. Do you see a decimeter cube written over here? As soon as we see decimeter cube, we understand immediately that this is volume. We're talking about volume. Now, we need to take the volume formula. So moles is equal to volume over molar volume. Now, the value of molar volume is always 24 for any gas on the planet. The value in the numerator actually comes from the question. 100 decimeter cube is written over here. That's how 100 over 24 is equal to 4.16 moles. Remember the rule, three significant figures and no rounding off in original parts. We actually only rounded off the final answer. So even if it seems to be 4.16667 on the calculator, you only take three significant figures out of the calculator. That is 4.16 mole. Are we clear so far?
Yes, sir.
Good. Then let's move to the second step. Now, the second step is moles of water produced. We need to calculate how many moles of water would be produced with this reaction. We already know that 4.16 moles of ammonia reacted with oxygen. Now, originally, the equation tells us that 4 moles react with 5 moles of oxygen and produce 6 moles of water. So ammonia and water are in the ratio of 4 and 6 as per the equation. But as per question, we don't have 4 moles. We actually have 4.16 moles. What happens then? So we need to find it out. So we put it as x, we write the dividing signs, and we change their places. X comes as a numerator on the left-hand side, 4.16 comes as a numerator on the right-hand side, and 4 comes as a denominator on the right-hand side. So 6 multiplied by 4.16 is the numerator and 4 is the denominator. Cut them out, get your answer. The answer comes out to be 6.24. You'll see that initially we were doing it incorrectly, and after a little bit of correction, we got to the right answer. So that happens. Don't worry if you get a wrong answer or if you make a mistake, because everyone can make a mistake. Once you get a hold of it, you can do it better then. So 6.24 moles of water are produced. Why? Because though the equation tells us that 4 moles of ammonia would produce 6 moles of water, but since we have used a little more, 4.16 moles of ammonia, so we have produced a little more of water. Instead of 6, we produce 6.24 moles of water. So what's the mass of that water? If the moles are 6.24, what would be the mass? So again, this is a formula step. And the formula is moles is equal to mass over mr. We rearrange that formula. It tells us mass is equal to moles into mr. Sorry for the smaller font. It's written like it's a messy writing, but what's written over here is actually mass is equal to moles into mr. Now, mr for water is 18. You can calculate it separately. 2 of hydrogen, that's 2. 1 of oxygen, that's 16. 2 plus 16 is equal to 18. So 6.24 moles of water multiplied by its molar mass, or mr, molecular mass, that's 18. The answer is 112.32 grams. So actually, with 100 decimeter cubes of ammonia, we produce 112.32 grams of water. That's where the footbridge helps us. We are actually inputting the volume of a gas and we are taking our output as mass of water. That's where actually Footbridge plays a certainly good role, actually an excellent one, to give us the quantities of reactants and products in two different sets of units, volume and mass, reconnecting them both at one point. I hope you understand the whole thing. Do you? But even if you're a little bit confused, don't worry. Even if you don't get a grasp of it 100%, you understand it up to 40% or 60% or 70%. I don't know what percentage you are going to rate yourself as per your understanding, but with more and more examples solved, the understanding would get better and better and closer to 100%. So much so, after solving a few examples, you will be very fluent with it. If you understand the first one, of course, a little bit, if not completely. Do you?
Yes, sir.
Good, good. Then try going with question number 2 yourself. If you get stuck at any point, do let me know. Does not matter whether you stuck with a certain part or whether you stuck with the whole question. Do let me know, and whatever is required, whether the explanation of the whole question is required or whether a certain part is required, I can always help you. Go ahead, take your time. Let me know when you're done. Okay, for the next topic, percentage yield and percentage purity of product. A reaction may not always yield the total amount of product predicted by the equation. There may be some loss, and the loss may be due to several factors. The first factor, reaction may not be totally complete. The reaction may not complete. The reaction may proceed up to 50% or 70% or 20% or just 10% or maybe to 90%. It may not complete forever. So you won't be able to produce as much product as you wanted to. Now, there may be any errors in weighing the reactants or products. Errors are actually to humans. Humans make errors. So there are some errors that are made by humans intentionally, and there are some unintentional errors. There are some errors associated with specific steps or the way or specific processes such as centrifugation or filtration or crystallization or distillation bound to have some certain differences based on errors. The errors can be totally human and because of the person is inexperienced, a student is simply learning through making mistakes. So yeah, there can be many sorts of errors. And errors are one of the big reasons why there may be a loss in the amount of product. Now, material may be lost in carrying out the reaction or in transferring or separating to products. That actually is reaction specific or process specific errors or loss in material. So percentage yield is the concept that I'm going to keep for now, but I'm going to go for percentage purity first. And this is very easy. It's one of the easiest concepts of this chapter and would hardly take a few minutes of learning curve. You will very easily learn it. The percentage purity is the mass of pure product divided by mass of impure product multiplied by 100. It's very much similar to the kind of percentage you use for your marks. For example, you take your numerator as marks obtained. Sometimes they're good, sometimes they're bad. When they're bad, we are sad. But let's go with the example of good marks. Okay. And the denominator instead of mass of impure product are the total marks. Let's say you have taken on a test, you have taken, let's say, 30 marks out of 40. So that's how you're going to go with the percentage. So we do the same with pure product and impure product, keeping in mind that the amount of impure product is usually more, and when we remove the impurities, the amount of pure product is usually less. For example, they have taken the example of the purification of copper, and they have put the example in this paragraph. Take a look at it. An initial crude or impure sample of copper, crude means impure, is prepared industrially. It is then tested for purity. 10.15 grams of a sample of impure copper was analyzed by various methods, and it showed that it contains 9.95 grams of pure copper, and the remaining mass is being made up of other metals, simply the impurities. So how do we take the percentage purity? Pure mass up top in numerator, impure mass down in the denominator, divide them, multiply by 100, you'll get your percentage. That's how easy percentage purity is. Get the point?
Yes, sir.
Then it's really easy. So we can simply stop sharing over here. We can get to a whiteboard. So I'm going to write the formula for you. So percentage purity. And I'm not going to exactly go with math. I'm going to keep it to amount. When I use the word amount, it means that I may talk about the mass, I may talk about the volume, I may talk about different units. So that's how it works. So when I write the word amount, it means it is representing a broader category of words, a broader category of units or quantities, right? And I'm doing it on purpose. By doing so, I actually allow you to understand more kinds of questions and deal them appropriately. One, two, it also allows you to understand one important point that when we are taking the amount of pure and impure product, it's better that you put up a rule. units in the fraction. I mean, the fraction given over here, pure and impure product, are supposed to be same or should be same. I shouldn't be writing supposed to, it should be same. Which means that if you're taking mass in the numerator for pure product, you should be taking mass in the same units for impure product in the denominator. For example, if you're taking grams in numerator, take grams in denominator. If you're taking kilograms in numerator, take kilograms in denominator, even if you need to change. All right. So even if you need to convert the units in from one quantity to another, please do so, but make sure the units in the fraction should be same. So gram up top, gram bottom, kilogram up top, kilogram bottom, decimeter cube up top, decimeter cube bottom. If you work that way, it's going to be really good. Let's do an example question. So 20.18 grams of crude copper, and since I've already told you that crude means impure copper, was purified electrolytically to 98.98% purity. Find the mass. Actually, mass in grams of pure copper. Now, since you've already done with the percentage in the simple way, okay, so I have changed the question a little bit so that you need to rearrange the equation in order to get your answer. Go ahead. Try to do it. Let me know the answer. Let me know when you're done. Have done the same. I guess you would be right. You have taken the percentage purity, and that is 98.8%. You multiplied it by the value of pure impure product, which was 20.18, and you divided the whole with 100 in order to get your answer for mass of pure product. If you have done the same and calculated it correctly, then your answer is right. Can you repeat your answer? It was 19 point? 19.93 grams, right?
Yes.
Mass of pure copper. Perfect. That's it then. I hope you get a hang of it, right?
Yes, sir.
Good, good. Now let's get back to the book. Okay, so I'm going to go back to percentage yield since we're done with percentage purity. So here's percentage. There you go. There's percentage yield. So percentage yield is actually what is produced in the reaction. Yield means product. And there are actually 2 to 3 different kinds of yield. The actual yield, which is actually produced in a reaction. Predicted yield, what you predicted you would produce in a reaction. This is basically done on paper. And the percentage of what you actually received, what you were expecting, and what you actually received. This is also more like your marks, all right? So for your marks, you do understand that actual predicted marks, actual marks, percentage marks is something that you can say. So for a test of 50 marks, let's suppose you predicted that you're going to get 48, instead you got 45. So if you take that 45 out of 48 and you multiply it by 100, so that's actually the percentage of prediction that you achieve. It works like that. The test is still of 50 marks. You predicted that you're going to get 48 and you actually got 45. So it would tell you the percentage of your prediction of what your prediction is true. We do the same with yield. So it's actually not completely explained here in the book. So I tend to actually explain it on whiteboard. So let's go back to whiteboard and let's explain it over there. So let's do it step by step. First of all, I'd like to explain what yield is. Yield is amount of that is actually amount of product produced. And if I talk about types of yield, so then number one is actual yield. So what is actual yield? Amount of product produced after an actual reaction. And secondly, we say predicted yield. We sometimes call it theoretical yield. Predicted or theoretical, both kind of yield means the same, and that's actually amount of product produced in theory or on paper. Like we're doing, we're not even doing any chemical reactions. Actually, we're not talking about a lab. We're not doing it in lab. We're not doing it in industry. We're not doing it in daily life. All we are doing is in theory or simply on paper. We're expecting it. It's also known as expected yield. It has different names: predicted, expected, theoretical, experimental. There are many names to this yield, right? And then there is the last type, percentage yield, the one on which our topic is based. So this one is actually formulated, and we formulate it as percentage yield is equal to actual yield over predicted yield or theoretical yield, whatever you'd like to write, into 100. Okay. So I usually tend to write it as AY over BY or ty into 100 in order to get your percentage. So this gives me the whole thing, and I tend to write it as percentage y. This is my shorter way of writing the whole thing. You don't actually need to do it in paper, but if you want to do it as a part of your rough work, it's entirely up to you. So I'm going to use the same symbols in my questions. It's easier for me to write, and students tend to explain the same thing. Now, do understand something really important that we have discussed. Predicted yield is always less than, actually, I made a mistake, not predicted yield, which is less than actual yield is always less than the predicted yield, because we tend to predict more. The actual is always less. You have been studying the same thing in physics by the name of inputs and outputs. Back in IGCSE, you studied that input is always greater, output is always less. Your output cannot be same as your input for most of the mechanical or other processes. That actually holds true for chemistry as well. So, and there are many reasons to it. Number one, reversible reactions. Some reactions get reversed and they don't never go to completion, all right? Or due to side reactions or side products. For example, the same set of reactants may react to give a side product. For example, if you're burning coal, now this is winter season, everybody's going to enjoy bonfires and barbecues. We tend to burn coal for this purpose. And when we are burning carbon and oxygen, we tend to go for the simplest reaction, carbon plus reacting with oxygen, giving us carbon dioxide and a lot of heat. The heat we tend to enjoy in harsh winters. Now, that actually goes sideways sometimes. Carbon may react with oxygen to produce carbon monoxide. Now, you already know carbon monoxide is a toxic gas. That is not the gas we wanted to produce, but due to a side reaction, it got produced anyway. So, another third thing is inexperienced worker. We can also call it as human error. Anyone can make an error. Anyone can make a mistake. No matter how experienced or how inexperienced, it can be completely unintentional and you may make a mistake. And errors bound with certain processes. Such as filtration, distillation. These are some processes in which they're bound to be less yield and than expected. You can't always have 100% of yields. So that's how it goes. This is the basic idea of all of it, to give you what yield is all about. To be honest, you won't be going through all of this. You would only be working with the formula for percentage yield. That's how it goes. Okay, so how to work with percentage yield formula? That's what we're going to do in the next sitting. All right. Any questions?
Right, sir. No, sir, it's clear.
All right. Okay.